This lesson we're going to look at linear quadratic systems, which means I'm going to give you a quadratic, I'm going to give you a linear, and you have to figure out where they intersect. So right now I've just got Desmos pulled up. I have one function, so my red function, that's my quadratic. I have my blue function, there's my linear, and for that one I set up a slider, so that way we could kind of see what's happening. If I move that line up and down, notice that it's crossing my quadratic at two places. Oh, no, now it's not touching. Okay. So we saw that we had two intersections, we had one intersection, if you were really quick you could see it, and we had no intersections. If I change my slope, so there's my m value, again we can see that it's intersecting at 2 points. Sometimes it'll be 1 point, sometimes it'll be 2 points. Okay, so if I dropped it down here, and if I started changing my slope, we've got two intersections, and then we have no intersections. So we're going to have a couple of different cases, and we have to be able to solve depending on how many cases we have to worry about. Okay, so like we said, we've got three possible scenarios. We have the scenario where my quadratic, sure, maybe it looks like that, and my linear, let's maybe make it look like this. So in this scenario, we have it intersecting in two locations. So we have two answers possible. Okay. And then we also have the scenario where it intersects only once. So this would be if the linear was a tangent line, which you'll learn lots about in grade 12. So it only intersects once. So I have one answer that is possible. And then we have the scenario where there are no answers possible. So this is where they just never intersect. So regardless of where your x and y axis is, what matters here is that there are no intersections. And if there are no intersections, then there are no answers possible. Okay, so just like when we had different options for our x-intercepts, we have the same scenario happening here, only instead of worrying about where the quadratic intersects the x-axis, we're worried about where it intersects some other linear function that we've given it. Okay, here I am going to follow example 2 from page 196, and we're going to figure out how many points of intersection there are for these two functions. So f of x is a quadratic, g of x is a linear, and the easiest way to do this is we're going to set f of x equal to g of x, because that's really what a point of intersection means. When are the two things equal? Take my two functions, so I've got 3x squared plus 12x plus 14 equals 2x minus 8. I'm going to bring everything over to the one side. So to do that, I have to minus 2x from both sides, and I'm going to plus 8 to both sides. I'm just going to do it all in one step. That gives me 3x squared plus 10x plus 22 equals 0. And this is really good because now what I can do to solve for how many intersections is using my discriminant b squared minus 4ac. Remember, if it is positive, then I have two intersections. If it is 0, then I have one intersection. And if it is negative, then I will have no intersections. Okay, so that means we need to figure out who our B, A, and C are. So it's alphabetical order. A equals 3 because that's my x squared. B equals 10 because that's my x. And C equals 22 because that's the number that has no x. So let's pop this into our formula. B squared minus 4AC. Figure out what that equals. So B is 10, so I get 10 squared minus 4 times A, which is 3, times C, which is 22. Throw that in your calculator or by brain. 10 squared is 100 minus 264. Final answer gives me a negative 164. So because my discriminant was negative, therefore there are no intersection points. So all I did was I just graphed the two equations from that example. So my red is my quadratic, my blue is my linear, and as we can see, there are definitely no intersection points, which is good because that's what we came up with. Okay, let's take a look at example 3 from page 197. So quite often what we get with quadratics is we get all these height things. Something gets thrown off the ground, shot off the ground, whatever. So in this case, we have a skeet, which is a quadratic. So it's following our quadratic curve. And then we have a bullet, which is going to follow, for the sake of the question, a linear. And what we want to know is when are they going to hit and how off the ground is it? So here, let's just zoom in. Before we go and do the actual algebra, if we look, we can see that it actually intersects here at a positive time and they intersect here at a negative time. The negative one we're not going to care about. That one doesn't matter. Okay. It'll be this one up here that we're going to want. Okay, and then once we find that time, because that's the time, that'll be our 0.5, that's our x-axis, we're going to sub that back into the equation in order to solve for the height, which is the y value. So that's the algebra we're going to do, but it does help sometimes to have that visual ahead of time. Okay, let's do the algebra here. We've got our quadratic function, which is our skeet. We have our linear function, which is our bullet, and we have to figure out when they meet. So to do that, we're going to set our two functions equal to each other. So we're going to say f at t is equal to g at t. So let's write the two functions side by side. So we've got negative 5t squared plus 32t plus 2 all equal to 31.5t plus 1. So we've just set them equal. Now we have to put everything over onto one side. So to do that, let's take these guys and put them over there. It doesn't really matter which one you do. So let's see, we're going to subtract 31.5t from this side, which means I subtract it from that side. And I need to subtract my 1. So let's subtract 1 from this side. And that means I have to subtract the 1 from that side. Let's see what we end up with. Okay, so let's finish this up. Let's see what we have. We have negative 5t squared here. 32 minus 31.5 just gives us 0.5t. 2 minus 1 gives me 1. And that's all equal to 0 because all of this stuff has already come over here. Now I have a nice new quadratic that I can solve. Definitely not factoriable, but that would have been one option, right? To solve for t, we could have factored it. Does not work in this situation. So instead that means we have to use our quadratic formula. Good thing we already know how to use that. To use quadratic formula, remember we need to get our coefficients. So let's figure those out. We know a is the coefficient in front of our t squared. We know b is the one that's in front of our t. And we know c is the one that has no letter attached to it. So there's my three coefficients. So let's sub them into our quadratic formula. So let's see, we got t, so t equals negative b plus or minus square root b squared minus 4ac all over 2a. Okay, let's sub it in. T equals negative 0.5 plus or minus square root 0.5 squared minus 4 times a, which is negative 5, times c, which is 1, all over 2 times a, which is negative 5. Simplify what's under the root sign first. Negative 0.5 plus or minus square root of, that gives me 0.25. Minus gives me a plus 20. All over 2 times negative 5 gives me a negative 10 in my denominator. So I now have negative 0.5 plus or minus the square root of 20.25 divided by negative 10. So I know that t is going to be these answers. So this is going to give me those answers. So we're going to just do 2 of them. Let's see. We've got t is equal to negative 0.5 plus the square root of 20.25, all divided by negative 10. Make sure you calculate your numerator first, hit equals, and then divide by negative 10. That'll save you your order of operations issues. that should give you an answer of negative 0.4. Now I need to do the minusing version. So t equals negative 0.5 minus root 20.25, all divided by negative 10. And when you calculator that one, you should get an answer of 0.5. So that's good. So now we've got two answers, and we wanted two answers. So we have the one from before things were shot. So this one is not applicable. Not usable, right? Negative time, can't do that. So that means positive time will be where they hit. Therefore, t equals 0.5 seconds when they hit. Now I can solve for my height. Okay, so we just figured out that they hit at time equals 0.5 seconds. So I'm going to sub that back into one of the functions. It doesn't matter which one because you're going to get the same answer because that's when they hit, right? We had our quadratic, we had our linear. There's where our timeline went. There's my time. There's my height. So I know that they were hitting here at 0.5 seconds. So the height is what we're looking for, and you're going to get the same answer. Doesn't matter which function you sub it into. The g at t, the linear one, is definitely an easier one to solve, so let's sub it into that one. So let's figure this out. G at 0.5 bracket equals 31.5 times 0.5 plus 1. Calculator, and you end up with 16.75. Therefore, they collide at 16.75 meters at a time of 0.5 seconds. So there we go. We now know that our height is at 16.75 meters. Time is 0.5. That's when they collide. There's my question. Okay, let's do one last example. So your textbook doesn't have one of these, but I am assigning one of these for homework. So let's check one of these. We need to find k so that the functions intersect at 1 point, 2 points, and no point. So very similar to what we did in our last lesson. We're going to set them equal to 0. We're going to use the discriminant, and then we're going to use the properties of the discriminant to help us figure this out. All right, let's set them equal to start with, because intersections have to deal with when the two functions are equal. Let's make them side by side. So we get 3x squared plus 6x minus 7 equals negative 6x plus k. And it's that k value that we're trying to solve for, but we're still following all our same steps. We're going to move everything over to the other side. So instead of minus 6, we need to plus 6x to both sides. And instead of plus k, we're going to minus k from both sides. So let's simplify this, see what we've got. 3x squared, 6 plus 6 gives me 12x. And then now I have this minus 7 minus k equals 0. All right. So now we need to use the properties of our discriminant in order to solve for this. So our discriminant, remember, is b squared minus 4ac. Okay. And to start solving, I'm going to start with 1 point, which means I'm going to set it equal to 0 for one intersection point. Okay. Figure out what our coefficients are. So a is 3, b is 12, and c is going to be all of this, because all of that is what's not attached to an x. So c is going to be equal to negative 7 minus k. All right. All right, let's sub in. So b is 12, so we have 12 squared minus 4 times a, which is 3, times c, which is this negative 7 minus k, all equals to 0. So let's simplify. 12 squared is 144, minus 4 times 3 gives me 12, bracket negative 7 minus k equals 0. So in order to keep going with this, we're going to want to expand our brackets. So we're going to expand just like we normally do. So we get 144, negative times a negative gives me a positive. 12 times 7 gives me 84. Negative times a negative gives me a plus. 12 times k. 12k equals 0. And all I want to do is solve for k. So that's fine. Let's put our numbers together, rearrange, and we've got it. So 144 plus 84 gives me 228. So 228 plus 12k equals 0. Let's move the 228 to the other side. So we're going to subtract it from both sides. So we've got 12k equals negative 228. Move your 12 to the other side. Right, let's divide both sides by 12. Okay, so to finish it off, we know that k is going to be equal to negative 228 divided by 12, which gives me negative 19. So now we've solved. All that's left is interpreting. So for one point of intersection, remember that was when we said that our discriminant, b squared minus 4ac, was equal to 0. That means g of x will be equal to negative 6x plus, instead of k, we now have 19. So it'll become negative 19. For 2 points of intersection, that would be when my discriminant is greater than 0. So I can take that whole equation that we just solved for. If I made all of those greater thans, there's no reason to have flipped it. We would only have flipped it if I was dividing by a negative. So therefore, this would work for all values of k greater than negative 19. Will give me 2 points of intersection. And likewise, for no points of intersection, that would happen when my discriminant is less than 0. And again, that would be when k is less than negative 19. So we've solved.